Hi, welcome back. In this lecture, I would like to continue talking about the fundamentals of a computer system. I will talk about the second component of the computer system, that is memory. In particular, I will emphasize the role of a memory subsystem in high-performance computing and what are the numbers that characterize the performance of memories and how we can optimize memory usage. At the end of this lecture, we will be able to describe the parameters that characterize the performance of the memories. We will be able to list and describe different kinds of memories and their technologies. We will be able to give numbers, that is, quantify the capacity and the speed of different kind of memories. Finally, we will be able to list different optimization techniques for effective memory usage. What is the goal of memory? Well, memories are used in a computer system to store bits. So bits can be our arrays, can be our arrays that are storing information about the pixel, for instance. Memories are, in computer science, are an abstraction, and the abstraction of memory applies to different kind of memory technologies and memory units, from the registers on the top of the processor to the caches, again still in the process world, to the main memory, the RAM, and to also storage technologies like hard drive and SSDs. What are the numbers that are telling us how good is memory technology? Well, it turns out that there are two numbers, that one is the bandwidth and the second one is the latency. As you can expect, when talking about high-performance computing, one major difference between all these different kind of memories is the speed at which they can read or write different data to the memory. As I told you, there are two important parameters that characterize the memory performance are the latency. Latency is the time that it takes to the device to find the data that's being used. How much time it takes to access one data. The second important number is the bandwidth. Bandwidth is the amount of data that is read or written per second. When talking about the bandwidth and latest parameter, is often useful to think about the faucet analogy. So the latency can be related in this analogy to the time that takes the time that it takes for the water to get out. It's a kind of a response time. So whenever we roll and open the faucet, there is some time that it takes for the water from our turn it on for the water to come out, right? So this response time is the latency. Once we started we turn it on the water, so we start the water, we have a flow of water coming out from the faucet. So this flow, that is amount of water that is exiting a certain surface per second, that is the flow, is equivalent to the bandwidth. Again, just to summarize, two parameters that characterize the memory performance: bandwidth, that is similar to the flow once we started, and then the latency, that is the response time. Right? So the response time we have to read and write the data is the latency, and the amount of data that we can move per second during the read and write operation is the bandwidth. So to make a little bit things more complicated, it turns out that the bandwidth and the bandwidth is and the latency is really depending on the way that the data is being read or written. It turns out that most of the memory units perform much better when we read the large chunk of data, like in one big shot, as opposed to many small chunks. So if you read like one big chunk of data, the bandwidth is going to be much higher than the bandwidth of reading several small amount of data. So this data access pattern, like a small data against big chunks, is referred to as sequential, right? When we read a big chunk of data sequentially, versus random access that we might want to read different part of, for instance, an array, but we are not accessing sequentially. Right? So sequential access is typically high performance, right? Performance, while random access is typically penalized in when designing high performance computing application. So what we will see that one of the optimization technique is try to store our data in blocks of data that we know that is accessed sequentially by the application itself. A second analogy for this lecture is the analogy of memory as a book, to describe the difference between sequential and random access. If the data in these memory units is thought of as pages in a large book, we will have we will see that most memory units will have better read and write speeds when going through the book page by page, rather than constantly flipping from one random page to the other one. Right? So if you read sequentially, our speed in reading will be faster, but if you access different page of the book that are not sequential, there will be time to turn the pages, and it will take more time. Now I want to describe different kind of memories and their technologies when we talk about computer system. Probably the most famous memory technology is the main memory on the computer. This is called RAM, that stands for read access memory. Random access memory. And this memory is used to store application code and data. So for instance, we allocate an array, and then the array will be stored in the main memory, the RAM. The RAM has a fast read and write characteristics and performs well with the random access pattern. So we have addresses, and we can go from one address to the other one. One limitation of the RAM memory is the fact that is somehow limited in capacity. Typically, the main memory capacity today is around 64 gigabyte range. There are different technologies that have been used to implement main memory. So one is probably the most common one, the most also used one on consumer grade computers are the DDR. So you might heard DDR4, DDR5 technologies. So you pull up like a desktop, you will notice this kind of system. This is our memory. Turns out that nowadays also HPC system are using HBM. This is a high bandwidth memory, so it's a different technology for main memory. So for instance, the most powerful supercomputer in the world, called Fugaku, instead of having DDR, is using HBM. That, as I said, high bandwidth memory provide higher performance in terms of memory bandwidth. The second kind of memory that are integrated on the processor are the register. A register contain working data. So whenever the processor is making computation, it accesses the data on the register. That's why we say is working data. So modern CPUs perform most overall operation only on data in the register. That means that the data needs to be in the register in order to do computation. Another kind of memory on the CPU is the cache memory. The cache memory contains a copy of the data that is on the main memory. In the cache memory we typically have data that is that our application use many times, right? So these are faster memory as smaller, and we try to have the data that we use several times in our application in the caches, because they're very fast and we can access this memory very fast. Caches are, as I told you, are faster but consume more space and power. Cache memory, they are typically different level that are characterized by different capacities, so the size and different speed. So closest and the smaller cache, and also the fastest one is called L1, right? L stands for level 1. We have L2 cache that is typically that is larger but also slower, and in many systems also we have L3, level 3 cache, also called LLC, that stands for last level cache. So these are memories that are on the processor are very fast. Let's look also other kind of memories. If we look at so-called storage, that is a persistent memory, one technology is that to store data are the so-called hard drive and spinning hard drive. So we have a bunch of disks that are actually spinning. Therefore, we call them spinning hard drive. So these are hard disks where we store our long-term data. They persist even when the computer is shut down. So the data in the caches, register, and the main memory, they just disappear as soon as we turn it off the electricity. In this case, the data is persistent, so that's why it's called a persistent memory. As you can imagine, the performance of this device is worse than main memory and cache. Right, so he has a slow read and write speed because the disk must physically spoon and move, and this takes time. This is the performance of the hard drive is highly penalized with the random access, right? Because we need to move the disk back and forth. But the major advantage is really the large capacity. So today there are hard disks that typically on 10 terabyte range. So one of the major issue though is that you see that many mechanical parts are involved on the hard drive, and that means that these devices are more sensitive to breakdown, right? So it's quite common to have some of these disks fail down because some of the mechanical components fail. A last kind of memory or a permanent memory, also called the storage, is the SSD. That stands for a solid state disk. So nowadays many of the laptops, instead of having a spinning hard drive, they do have an SSD. So the laptop I'm using now for this lecture is having an SSD. So it's similar to a spinning hard drive in the sense that the data is stored permanently, so it's still there when we shut down the laptop. He has a faster read and write speed compared to the spinning hard drive. However, have a lower life expectancy than a hard drive disk. It turns out that after many cycles of read and write, the SSD degrades. It's also typically much smaller in capacity. It is typically 1 terabyte range or less, so half a terabyte range. However, is today highly involved, heavily used in consumer grade hardware. So let's look at the performance. So here I have for plots On the x-axis, we have different technologies from a hard disk, solid SSD, main memory, and caches. On the y-axis, we have a different performance characterization number. The important part that I want to emphasize here that all these plots are actually a logarithmic scale. That means that even a small difference in this plot is actually a big difference. So log scale, small difference in the plot might also mean that the difference is also quite big. So the first point I want to make that I already mentioned is the difference in capacity. So we go from a hard disk that can easily reach 10 terabyte to L1 cache that and the size of kilobyte and megabyte size. The second performance number, we say that we use the bandwidth to characterize the performance of the memory system. We have two kind of bandwidth. One is the read bandwidth, and the other one is the write bandwidth. It turns out that reading operations are typically faster than write operations, so we often call about performance asymmetry between read and write operation. As you can see, increasing the size, increasing the size of the memories, the bandwidth decrease. Right. So if we see that spinning hard drive has a small bandwidth, but has a large capacity. In general, we see a clear visible trend that is the read and write speeds and the capacity are inversely proportional. So that means when the capacity goes down, so the size goes down, the bandwidth they go up, right? So they go up, both the read and the write operation go past. That basically means that as we try to increase the speed, the capacity is reduced. That means that in this case, small memories are very fast, big memories are quite slow. Lastly, on this plot, we see the latency of the system. We go to, so in this case, the unit is a millisecond. We're around here 10 to 26. So this is roughly tenths of a nanosecond. Right. So the caches are around 10 to nanosecond latency to access a cache. You see that the hard disk in many cases is around 10 microsecond, and that is a huge number in a computer system. Right. So to read from disk takes quite a lot of time. This is the response time we talked at the beginning. SSD that we are using, for instance, on this laptop is 10 to the minus 1, so roughly 1/10 of a millisecond. Still big number, much better than the hard disk. So why I say big number and small number? What I refer to. So here we say that 10 nanosecond is small. When I talk about relative scale, I always think about the computing scale. We talk about how to characterize the performance of the CPU, the processor. We say that we have the clock cycle, typically in the range of the gigahertz. That means that we can do an instruction in a nanosecond. So when I talk about this number, I'm confronting them with the time that takes to make one instruction. That is basically order of the nanosecond. As you can see, today memory is becoming a big bottleneck, right? Because only to access data, it takes more time than actually performing in instruction. If the data is in the caches, then we can get good use of the computation that is order of nanosecond. However, if we need to access data on the RAM, you see that we are paying some penalty here, and basically our processor is just waiting for data, right? Because the to read and write to this memory is relatively small, much higher than actually to do the computation. So as you saw in the previous slide, you saw that we are basically building this memory system, tiering, composing with the different memory layer. We start from a very fast memory at the register and the caches. The caches might have different layers from L1, L2, and LLC. So all the modern system implement a tiered approach to the memory, where tiered means that we have multi-levels. In general, data starts in the full state in the hard drive, and then part of it moves to the RAM, and then a much smaller subset of this data moves to the LL1, LL2. Whenever we need to be used by the processor, it's moved to the register. So this method allows us to have programs that are efficient, following the principle that we keep memory in different places depending on the access speed and requirements. What I mean with that? I mean that if I have data that I keeping reusing, like for instance part of the array that I keeping doing the computation on, we want that data on the fast memory because we used a lot. If we have data that we don't use so often, we might want to have just on the RAM, and then put on the cache only when we use it. So we want to have the so-called hot data on the fast memory, and the cold data that we don't touch much on the slow memory. What I said in the previous slides connected to the topic of this slide, that is optimization for memories. So when we optimize the memory patterns of the program, there are different things that we can optimize. First of all, we can decide the data placement. So which kind of memory we want to place our array. And this particularly done in many cases using specific allocators if we have different memories available. As I told you, we want to keep hot data, the data that we use a lot, on the fast memory that typically is small. A second consideration to do when optimizing for memory is how the data is a layout. We want to increase large sequential reads because those have a high performance. And how we can do that? Well, we can reorganize the data layout of our data. So for instance, a technique that are widely used in an HPC are, for instance, taking an array and then dividing in small blocks, for instance, called tiles or block. So technique like blocking and tiling allow us to divide our data in small tiles that fit perfectly certain capacity of a certain memory. So for instance, we can design data layout that fit perfectly to different caching level in order to suggest the usage of the caches. So data layout is an important aspect when doing HPC. And of course, also we might want to look at how the data is accessed in our algorithm, in our code. So we can arrange the flow of our program so that we maximize the reusage of data. For instance, if we have one array, we start using an array, we want to still keep working on that array so we can maximize the probability that we have data on the cache. There are other techniques that allow us to improve the performance of data movement and the memory usage. One is called asynchronous I/O. That is nothing else than saying that we are trying to overlap memory operation with computation. So whenever, for instance, whenever we can overlap. So for instance, we have a memory operation, we do the computation. In the meanwhile, we can do another memory operation. Of course, the compute part doesn't need this memory, so we need to be clever how to organize this memory operation. But asynchronous I/O and asynchronous data movement is a basic technique to allow to do computation and data movement at the same time. A second technique is actually to the so-called preemptive caching, that is generating a cached data version before they are requested by a user. We can explicitly create some software cache and unfill it before we know that they're being used. So for instance, many framework such as framework for machine learning, deep learning like TensorFlow, they provide a software cache that can be filled. If there is certain data that we know that we're going to reuse it, we can just cache it in this software. So this caching mechanism, also software, provide ways to make sure that the data is always where it needs, without having to waste some computing time to move data back and forth. In summary, this is this last slide. We focus on a few points. The important point when looking at the HPC memory system is to understand that the memory performance is characterized by two basic numbers. The first one is the bandwidth, and the second is the latency. When talking about these two numbers, it's quite useful to think about the faucet or pipe analogy. The latency is the time that takes for the water to come out from the faucet when we switch on. So this is more like response time. And then we have the bandwidth, that is the flow that is corresponding to the flow. So there is amount of water that is coming out per second once we start the water. The second point is that the memory performance depend also on how we access data. So it's not only depending on hardware consideration like the bandwidth and latency, but also how we access data. It turns out that read large chunks of data is faster than reading small data many times. We look at different kind of a memory system. In particular, we look at the main memory, random access memory, RAM, caches, register, spinning hard drive, and SSD. When we look at different quantities like capacity, bandwidth, and latency, we saw that the size of the memory is inversely proportional to the bandwidth. That means that small memories are very fast, while large memories are slow. Finally, we just did a few consideration about optimized usage of the memories. Optimization for memories include data placement. So we want to have data that is hot, that we use a lot of times in the fast memory. So data placement is important. Hot data on the fast memory. Second technique is looking at the data layout. So we might want to change the data layout of an array. For instance, we can divide in different tiles, each tile of the size of a given memory. And finally, also we look at rearranging the algorithm to reuse, for instance, a certain array many times. So we know that the array is on the fastest memory, for instance, caches. Finally, we also look at the possibility of some technique that we are also going to look at later on in the course, doing things in practice. A main one is to overlap communication, the read and write operation with the computation. This goes under the name of asynchronous I/O, or implement some software caches. So we store data that we know that we're using in special array that we call them caches. This is the last slide, and talk to you soon.